Physics students, welcome to the second video in topic 11.1, electromagnetic induction. In the previous video, I talked about wires and conductors moving in magnetic fields and how by virtue of there being a velocity vector that's perpendicular to a B field, that you could actually induce a current and induce what's called an electromotive force, or a potential difference between two ends of a wire. Okay. Again, it seems like you're getting free energy out of nothing, but in effect, it would take energy to move that wire, right? So I just want to talk about, remember, the concept of conservation of energy is very important and holds in all of these later topics in the course. I want to talk in this video about induced EMF and something called Faraday's Law. And now we're going to talk about the idea of a time rate of change of flux. Remember when we talked about flux before? I introduced it to you in the previous video. And I said often flux is associated with a time rate of change or a derivative with respect to time, if you know that function. Now we're going to talk about that, okay? And it turns out that a magnet moving near a closed loop creates a current in that loop. Now the loop has to be closed, okay? It has to be a circuit. But you can see from this PhET simulation here that as I move the magnet in and out of this particular cross-sectional area, there ends up being a magnetic force on the free electrons in that wire, which of course is a current. Now a couple other things. Notice how when I move the magnet back and forth, and we'll do this in class, we'll do examples of this in class, depending on the direction, depending on which pole of the magnet is entering the cross-sectional area, that has a great effect on the direction of the current. We're going to talk about all of that, okay? Now it turns out that there's an increased current as we saw in class, if I use a stronger magnet, so the B field is greater, the magnet is moved faster, so the velocity is greater, okay? And there are multiple loops of the wire or more turns, okay? Also, if the loop is made bigger, I could actually increase the current in that wire, okay? So different ways. You could also change. You could also change the shape. You could change the shape of the wire, make it bigger, make it smaller. There's all kinds of different things that you can do, which will influence the current in that particular wire. Okay. The other thing is that I talked about before was the orientation between the velocity and the B field. So if you're coming in with your magnet at an angle, right, you're going to get less of a flux and therefore less current than if you came in straight down at 90 degrees to the actual plane of the loop, okay? So obviously the following are true. Number one, the changing flux, we're talking d phi by dt, creates a current inside a conductor. Number two, it creates an E field inside the conductor. And number three, it creates a potential difference across the conductor. All of this leads to the fact that there is a current that flows through that conductor. And this is called Faraday's Law. This quantization, a way of quantifying d phi by dt, is called Faraday's Law. And it says that the induced EMF, okay, which is epsilon, is equal to the time rate of change of magnetic flux through enclosed conducting loops. Often n is 1, okay? So it's d phi by dt. As we saw last time, phi is Ba times cosine theta. So it's d by dt of that quantity. There's a negative sign, which is actually important, but we're not going to worry about it right now, okay? All right? Note also that a Weber per second is a volt, okay? And remember when I told you last time that you should be able to show that this equation gives you a volt. Well, in fact, it does, and it should show you that a volt is a Weber per second. So the induced EMF is the negative rate of change of the magnetic flux, okay? And the negative sign, like I said, is important, and we'll find out why that is later. I don't want to talk about that negative sign right now, okay? It's a little bit complicated, okay? All right. What this means is that there are three possibilities for inducing an EMF. And we're going to assume that only one variable is changing at a time. Otherwise, how would we quantify the effect of changing that variable on the induced EMF? Number one, what we can do is we can change the magnetic field, in which case the induced EMF would be of this form, dB by dt. Number two, we can change the cross-sectional area, in which case we'd have a dA by dt. Notice that in each of these, we'd have to quantify, we'd have to know the function of the magnetic field as a function of time, B of t, and the cross-sectional area is a function of time, A of t. There's almost always a way to figure this out if you're not given it. The third case, which is actually the most interesting and the most complicated, is we could consider theta t. If we know the rate at which the angle is changing with respect to time, we can take that derivative with respect to time, and that would give us the induced EMF. Okay, so in this case, this PhET simulation, the angle and the B field are changing. So in real life, this is often much more complicated. You see that? So the B field is changing because not only are the field lines getting closer together as the North Pole approaches the plane of the loop, field lines are closer together, but they also curve. So you can see it's actually quite complicated. Normally, at least in this class, we don't consider the function n of t. We don't change n usually. That's a constant. Now, sometimes you might have 1 loop, 5 loops, 10 loops, but it doesn't change. I mean, if you think physically, how would you add loops or take away loops? That would be kind of complicated. It doesn't really happen often in real life. Okay. Often in the IB, you see situations with sliding conducting rails, and this is actually a really cool analysis. Okay, so you might want to take some notes on this and really follow my logic here for this. Okay, so imagine that I have conducting rails, like a wire here. Okay, we're going to neglect friction, of course, and I have a conducting rod of a length L, which at t equals 0 seconds is right here. Okay, now imagine that the rod in a certain amount of time t slides from this position all the way over to this position. Okay, given that the magnetic field in this case is into the plane of the page. Okay, all right. Now, first of all, my first question for you is there a magnetic flux? Of course there is, because there's a closed loop, which is this initially just this area right here. Let me get my pen here. It's initially just this area right here, right? Okay. Now, what is changing with in terms of magnetic flux in this problem? Well, it's the area, right? The area goes from this little bit to this entire big bit over here, right? Okay. Now, I want you to notice that we're gonna have the rod sliding at a constant velocity, which is going to make the problem easier. Okay, v is a function of t. Okay, and it's dx by dt. Okay, x of t is the distance between the two positions of the rod from 0 to t. Okay, so in this case, the area is changing, and the area is changing according to the following function: x of t times L. Right? Okay, because v equals x equals x over t. Okay, so now the change in flux then becomes, I use this version of it where I'm taking dA by dt, because now I know what A is as a function of t. Okay, and I have that it's negative nb cosine theta d by dt of x of t times L. Okay, all right, well, x of t times L dx by dt is just v of t, so that would be negative v bl. Well, guess what? That's from Faraday, right? It says that the induced electromotive force is equal to n times v times b times L. Okay, so that's sort of a corollary of Faraday's law. Okay, and remember that the induced EMF is BLV, so this is really the same thing. So essentially, what I've done for you is I have derived Faraday's law kind of through the back door, I guess you could say, kind of from the other end. And I told you it was BLV before, the induced EMF, but Faraday's law really, this example here really sort of quantifies that and proves it. Okay? All right, try this example on your own. Okay, so here's the sliding rod. Okay? Length 20 centimeters, placed in a conductive railing, pushed to the right, constant speed, the induced EMF. Pretty simple, right? E equals BLV in this case because everything is orthogonal. Okay, 0.48. Okay, and I want you to note that by Faraday's law, the induced EMF is negative d phi by dt, negative d by dt BA cosine theta, right? And of course, dA by dt, as we saw before in the previous example, is just v, and everything is orthogonal. So the cosine of theta is 1, so it's BLV. Okay. Okay, try this one. Okay, now we're changing the angle. Okay, so I would use this version of Faraday's law. Actually, we're not changing the angle. The angle is constant, and we're changing. We're changing the B field. So that would be dB by dt. We know the rate at which it's changing. I get 0.4 volts here. Okay, all right. Now, in example 6, I was getting ahead of myself. Example 6 is where we're changing theta, okay? So pause the video and try this one on your own. This is a really good one. So a flat coil of wire has an area of 200 square centimeters, 50 turns, so N is 50, constant B field. Now I'm changing theta. So theta is a function of t, and I'm telling you that it goes through an angle of pi over 3 radians in 0.1 seconds. Calculate the average induced EMF, okay? Well, the average is going to be, well, first of all, using Faraday's law, the induced EMF is negative N d phi by dt, okay? The average would be negative N times this quantity, right? Times the value of the flux at t minus the flux at t naught minus or divided by the difference between those times, okay? So if you plug in all the numbers, you get plus 0.9 volts, okay? And remember how I told you that the negative sign is not important? You can see actually here how the negative sign now becomes important, because if we neglected it, we would have gotten 0.9 volts. And what does that mean? It means that whether the potential difference is positive or negative depends on in what direction the charge flows. But we'll talk more about that later, so don't worry about that right now, okay? All right, some pretty cool applications of this, all right? In this case, and we're going to try to build this in class, which will be really fun. Okay, you see, so this is an experiment where someone has taken a soda bottle and cut it and put this rod going across, and they've taped some magnets on this rod. And around the soda bottle, you have a whole bunch of coils of copper wire, and they're connected to an LED, okay? And what happens is when you're actually changing, this is Faraday's law in action. What you're changing here is you're changing the angle between the magnetic field and the plane of the coil. And every time you do that, the LED lights up because you're creating a current through that wire, a potential difference, okay? One thing to notice, the induced EMF goes back and forth between positive and negative periodically, and that's really important for us in the future. Therefore, the current switches direction periodically. It goes back and forth. And this is called alternating current. Remember, all the current we've talked about so far in this class with our studies of circuits and batteries and things like that, that was called direct current, DC, okay? So now we're dealing with alternating current. It turns out that all the electricity that's generated in the world for industrial and household and commercial use is alternating current. And again, we'll talk about that more in topic 11.2, okay? Now, what you should know right now, this is like, you take a step back and look at the whole big picture of this. The majority of electricity generated worldwide is made this way, okay? So this is quite a sweeping statement. What you have in these big power plants, okay, is you have these huge magnets and you have these huge coils that are made to rotate through the magnetic field. And then there's a way where you have these things called slip rings. Basically what it does is it makes a current, and that current carries electrical energy away, and that's using transformers and other ways of transporting that power, which we'll talk about later, gets spread out to various places for use, okay? So the key in terms of generating electricity and electrical power is to figure out a way to turn that coil in that B field. That's the whole point, okay? Now, there are lots of different ways to turn that coil. You could have hydroelectric power, right? You can have hydroelectric where the gravitational change in gravitational potential energy of water falling could turn that coil. You could, but the vast majority of electrical power generation is done by boiling water and having that steam rise and go through turbines and turning those turbines. So like coal-powered plants, the burning of coal, all they're doing is they're just heating water and boiling it. Even nuclear power plants, what's happening in those is that you're just boiling water, and that steam goes through those turbines and turns that axle. It's rotating that axle mechanically. Pretty cool. So here's a picture of some huge magnets in a electricity generating facility. Okay. Sometimes you see, like, on an electrical device, you can check this right now, whatever electrical device is near you. In the USA and Canada, typically electricity is rated at 60 hertz. That's what that means. It means that all the electricity generated, at least in the North American continent, those coils and all of those power stations, all those electrical stations, those coils go around 60 times per second between those magnets. Pretty cool. In many other countries, it's 50 hertz. Okay, so that's what that hertz means on your electrical rating of your device that you're using. Okay, a little bit more on changing theta, and then I'll finish this video. Okay, all right. We said that the induced EMF by Faraday's law. If we're changing theta, it's negative NBA d by dt cosine theta t, okay? If I carry through the derivative, notice that the negative sign goes away, and I end up with NBA sine theta t times d theta by dt, okay? Now, this is a way that I can solve this problem actually using calculus. And by now, you guys all know, hopefully, how to differentiate trigonometric functions, cosine and sine and tangent, okay? So try this example before we end this video. Okay, so the B field through a double loop of area 0.2 meters squared is a constant 4 Tesla. The angle is changing at pi over 4 radians per second. Calculate the induced EMF at 5 seconds. At exactly 5 seconds, remember the previous problem I had to talk about the average induced EMF. Now I'm talking about the induced EMF at exactly 5 seconds, okay? Because it's periodic and it's a trigonometric function, it's not constant, right? And I'm assuming that at t equals 0, the angle is 0, okay? Well, in this case, phi of t is omega t, right? And remember, omega is pi over 4 radians per second. That's the angular velocity, okay? Now, the induced EMF would then be negative d phi by dt of all of that, but as I found up here, that's NBA times omega times sine omega t, right? Okay? And I end up with negative 0.89 volts, okay? Because I'm putting in, here's where the time comes in. Here's where the time comes in at 5, okay? All right. At t equals 5, the loop is oriented at pi over 4 to the normal. It's really 5 pi over 4 radians, okay? So if you should probably get a piece of paper and think about how that loop in that amount of time, where it's changing and what the actual orientation is between the plane of the loop and the B field,